SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Power Plant System Engineering, Module 4, that is Hydro and Renewable Energy Power Generation Systems. So, in the first component of this module, we will focus on hydropower systems, part 1. So, in this hydropower systems or in this lecture, we will try to give some glimpses of hydroelectric power plants, its components, what are the different elements that are the part of this hydroelectric power plants, and most important features is that hydraulic turbines, which is the main backbone for these hydropower systems, in which power is developed from water. And one such turbines is a Pelton wheel, and we will discuss about the fluid mechanics and theoretical aspects of this Pelton wheel concepts and how it becomes useful for harnessing water power. So, let us try to see the feasibility of water power. What does this mean? Now, if you look at the power which is available from the water, and we normally call this as hydraulic power, one can write a fundamental equations like power available from water, density multiplied by if something like potential head or potential energy available in water. That means, we are keeping some slug of or some quantity of water at a certain height, and looking at the density of water is 1000 kg per meter cube. If you increase Q or H, then we can have enormous number of power which can be available from water. So, what it means for us is that if you try to make this water for electrical energy conversions, then one can write a fundamental equations, that is W is equal to G means 9.81, Q H, and we include some term efficiency, and T is the operating time in hours. So, what it means that by increasing Q and H, and if the turbine can operate throughout the year, that is 8760 hour per year, then we can see that this quantity is very huge. So, in other words, we can say there is certain feasibility of water power if it can be harnessed properly. Then let us look into the possibilities how we can harness. One way to look at that, when we have rain and it is falling on hard surface, then we have its potential energy availability when it rains, and rainwater proceeds towards ocean through in its path through its rivers. So, if we can see that river is available at certain height, and if you can take that slug of mass of water or the quantity of water is taken as the volume flow rate of water, then we can use that height of the reservoir or river to harness the water power. And that is the reason, since we do not require any kind of fuels, we call this as a natural available energy source. So, the theme of this hydropower plant is the energy of water is being utilized to drive the turbine, and in turn it produces the electricity. And next to the thermal power, the water power is the next level power production unit, and we call this as a hydroelectric power plant. And till date 20% of the total power of the world is made by hydropower stations. Now, looking at these things, if you see that what is the different advantage of hydroelectric power plants. So, basically their water is perennially available and in most of the rivers as well. Since there is no fuel is required, then you can call it as a white coal. It is a renewable form, or we call this as a white coal. The running cost of hydro power station is very low as compared to its competitives like thermal and nuclear power stations. There is no concept of pollution. Modern hydro generators have high efficiency over considerable range of load variations. That means hydroelectric turbines can be switched on or off in a very short time. Hydropower is emission free and they does not produce any greenhouse gases. The concept of hydropower plant is very simple, and its system reliability is much greater than any other power plants. Hydropower plants have a very greater life expectancy. That means, if you install a hydropower station today and assuming that water will be available or the river will be existence for another 50 years, then we can think of its lifetime. As long as the water is available, we can think of its life expectancy is about 50 years or more, as compared to any other competitors like thermal or nuclear power plants. Hydropower plants are ideally spinning reserves and it can be integrated with other power plants. It provides the geographical ecosystems, that means with benefits of irrigation, because we need to store water through a dam. Depending on the requirement of irrigations, the water can be controlled. So, it helps in afforestation, navigations, aquaculture, and being simple in design and operations, hydropower plants do not also require any skilled manpower. So, there are many advantages, but there are some loopholes or demerits, because the hydropower generations incur very high capital cost with low rate of return. That means, if you want to the entire infrastructure which is being invested, it is requires almost 15 to 20 years to get back the return, and this power station is highly dependent on the quantity of the water which is available. And moreover, hydropower plants are site specifics, and because of these reasons they incur transmission losses, since because somewhere there will be grid available, but we have to but the hydropower plant has to be located in restricted sites. Many a times the hydropower plants may disturb the ecology of the systems. So, emphasis is more given for small, mini or micro hydel power stations. Instead of thinking of large power stations, people nowadays think of mini or micro hydel power stations. So, this is some of the schematic diagram which says that if you look at mini or micro hydel power stations, we can imagine to have water availability in a pond, construct a dam, allow the water through some pipes, and it goes to the turbine and powerhouse, where we can harness this water power. So, available head for this we call this as a water head. So, such a simple concept can also be utilized through micro or mini hydel power stations. Now, let us look into the complete features or elements of these hydroelectric power plants. This figure shows the schematic diagrams of a or layout of hydroelectric power plants. What we see is that there are the catchment area. So, it is the big area which is available, and for which maybe you can say it is a river area in across which the river spreads with a very steeper slope, because we need to have a slope or free fall of water. So, we require some slope, and also we need to in which a dam can be constructed. So, in a catchment area of river we can think of a reservoir, and this reservoir will be located across a dam, and controlled water can come through the sluice gate or valve through pipelines, and that we call as a penstock. That means, in hydropower terminology, we call this the penstock. It is simply the water pipes. Then through this penstock it goes to the turbine end. So, here this turbine end we harness the power, and then it can be integrated with alternator, for which electric power generation can be possible. Then the discharge water has to be going through the tail race. Tail race means is another kind of catchment area where water is being discharged. One most important thing is that the water has to pass through a draft tube, and this draft tube has a very significant component of this power plant unit, because it creates a necessary controlled pressure difference upstream and downstreams, and water has to go in a smooth manner to the tail race. So, with this objective, so that necessary it does not incur many hydraulic losses. So, these are the essential components. So, I explained about the catchment area and dam. Then we have the reservoir. These are like natural water bodies, river or lake. Dam has to be constructed. So, this has to perform the, because this dam is required, because we need to have continuous operation of the turbine. So, we need to have a storing capacity. That means, we must have an estimates how much water should be available, or volume flow rate of water is available, while maintaining appropriate head. So, one can think of a dam to have a moderate head with large storage capacity, or high head with small storage. So, these two things possibility way we can think of while constructing a dam. Then the next important component is spillway. Now, when water flows through this penstock or dam, and in some cases when you say that stability of the dam is in danger, then we should have provisions for this reservoir basin to dispose of some of the water. That means, excess water should be relieved, and this is relieved through a structure which is called as a spillway. So, it in general it provides structural stability to the dam without raising the reservoir water to high flood level. Then the passage of water in a channel known as head race, and it leads to the water in a conduct. Now, this conduct, that means, when the water comes from the dam to the turbine, the possible ways that we can think of, we can think of a closed passage, typically a penstock or pipe, and we call this as a conduct. Now, through this conduct, what does it mean is that there is a regulated pressure difference which is maintained between, because since it is a closed conduit, it is a regulated pressure difference between the reservoir end and turbine end, that is maintained. Other possibility option is that we can open up this penstock. That means, we can think of the penstock as a channel, open channel flow from the reservoir end to turbine. So, it's through by assigning suitable slope for the passage of water. So, in a manner that way we call this channel have two components, one is head race, other is the tail race. So, in that case what happens, that entire flow through this open channel flow is almost atmospheric. So, that is another kind of possibilities we can have while thinking of for the passage of water from reservoir to turbine end. Then we have other components like a surge tank. So, surge tank is nothing but a small reservoir in which water level rises or falls to reduce the pressure wings that are when they are not transmitted in the closed conduct. That means, when we have a penstock or closed conduct, that means we have a controlled pressure difference. Now, let us assume that the water is passing through a open channel, or it is a lake, or in lake. In that case, sometimes when there is a reservoir basin has a very high water, then of course, the quantity of water in the lake will be also high. So, a surge tank is required so that it does not allow excess water. And most important component here, the draft tube. So, it is a draft tube is a divergence configurations in which is made when the water is discharged from the turbine. So, this diffuser action for the draft tube regains major portion of the kinetic energy or velocity of runner at the outlet, which otherwise would go as a waste or exit. Then last component what we call as a powerhouse. So, it is nothing but the stable structure which has all types of plant equipment like hydraulic turbines, electric generators, governors, valves, storage batteries, switchboards, etc. Now, let us see that how hydropower plants can be classified. So, the classifications are normally done based on the availability of head. One can think of high head, medium head and low head, and this also can think of the link to the quantity of water availability, high discharge, low discharge or medium discharge. So, accordingly we can say that we can think of mini or micro hydel power plants, a runway, river without pondage, with pondage, storage reservoir and all. The other way of classification is the nature of load, that is base load or peak load. That means for what circumstances, whether the hydro power plant is designed for simple base load operations or it is required to cater the peak load, that means at the time of demand it can give the excess power. So, that way we call this as a nature of load, electric load, which is linked in this alternator, or this alternator is again further integrated to the turbines. Then we have like for example, to give some estimates, if you think a mini power plants, it operates with a height of 5 meter to 20 meter and it produces a power in the range 1 to 5 megawatt, while micro power plants they work under a head below 5 meters, but they produce the electricity range from 0.1 to 1 megawatt. But in any case we can go for maximum energy resources from the water, we can go up to 20,000 megawatt. That means, it is a very highest structure or it is a large scale hydroelectric power plant. Now, let us move on to next segment, which is hydraulic turbines. In fact, it is the backbone of hydroelectric power plants because they convert potential energy of the water into the shaft work, which is in turn coupled with the electric generators for producing the power. So, historically hydraulic turbines are derived from water wheels. So, initially there was no concept of water turbine, hydraulic turbines, rather people used to call as a water wheels. One such name comes up like a Pelton wheel, but with more developments has happened in recent days, and based on that the hydraulic turbines are classified with difference in the elevation of water surface available between upstream and downstream of the turbine. And here if you look at this particular turbines, if we have the reservoir for which and we have the tail race means where water is discharged, that means the storage at this point and dispose of water at this point. So, we call this as a gross head. Now, coming back, water comes through certain pipelines. So, that is the reason it is we call this as a hydraulic grade lines, in which it incurs a loss of HF. So, ultimately the net head which is available to the water is H, which is nothing but the gross head minus HF, hydraulic loss. So, under this head, and that head is varies in the range from 2 to 2000 meter. So, when it is low head we say 2 to 15 meter, when you say medium head it is 16 to 70 meter, when you say high head it is 71 to 500 meters, and very high head means above 500 meter. So, more or less we can say 2000 meter is the topmost level in which the potential energy of water can be available. Now, depending on the availability of the flow, the turbines are classified as low turbines, and we call, and one such case is a Pelton wheel, medium availability of the flow and high discharge flow. So, we have Pelton wheel, Francis turbines and Kaplan turbines. And apart from this, the hydraulic turbines are classified based on the head and quantity of the water available to us. A second category is the working principle of the blade, that is what we have said, I have mentioned earlier, that when we say that passage of the water through a penstock or controlled manner, so entire slug of water goes and hits the turbine, and that are used for harnessing water power. This is one way. Other way to look at is that whatever potential energy available in this water, in this reservoir, first it is converted to kinetic energy by passing it through a nozzle, and this kinetic energy is used to strike on blades or buckets or on a wheel that rotates. So, that is another concept of working principle. Another way is that direction of flow of water, that means initially it can be radial and final entry for the outlet from the turbine could be axial, or it may be vice versa, or it can be a mixed flow. So, depending on the direction of the water flow, it can also be specified. Depending on the axis of the shaft and also depending on the specific speed. Specific speed decides whether it is a very slow runner, that means, or it is a very fast runner. So, whatever I have explained, this has been noted down here. Based on the mode of conversion of potential energy of water into shaft work, the turbines are classified as impulse and reaction turbines, and in impulse mode the available head of water is converted to kinetic energy in a nozzle, and then the water shoots out from the nozzle as a free jet at atmospheric pressure before and after the striking the vane of the turbine. Now, another way of looking at that, when the entire flow of head which is available in the reservoir, they are used to pass through a closed conduct, then it works in a reaction mode, and in this reaction mode a controlled pressure difference is maintained, and here the water is simply guided to strike on the blade. So, there is no conversion of the potential energy to kinetic energy in between. So, that is called as a reaction mode. We will try to explain subsequently for this impulse and reaction concepts. Then depending on the orthogonal directions of the turbines, then it can be considered as a radial flow, which is a Francis turbine, axial flow like propeller and Kaplan turbine, and tangential flow for Pelton turbine with respect to wheel, and the shaft axis refers to the axial directions. Now, when the flow at the inlet is radial and axial is outlet, then we call this as a mixed flow. If the flow is neither parallel to axis nor perpendicular, then it is moves as an angular direction with respect to axis. So, we call this as a diagonal flow. Such an example is Derais's turbines. Now, turbine shaft can be either vertical or horizontal. So, Pelton turbines have horizontal shaft, while other turbines have vertical shafts. The last feature of classification is through specific speeds. More details about the definition of the specific speeds we will discuss in the subsequent class, but what the bottom line or importance of this specific speed with respect to physical significance of the turbine is that the low specific heats denotes slow runner and high specific speeds denotes fast runners. So, this is the overall complete classifications which is shown in these tables for the water turbines. We can say there are 4 category of turbines: Pelton, Francis, Propeller, Kaplan, Derais turbines. They, depending on the flow directions, they can have a tangential flow, radial, axial, diagonal flow. Based on the specific speeds, we can say slow, medium and high. So, in the slow range we have Pelton wheel, we have Francis turbine, we have Kaplan turbines. Then the classifications based on the size of the turbines, we can have maximum head, maximum power, maximum diameters, and specific speed also can be here. So, we can in these things we can say Pelton turbines are low specific speed, where Kaplan turbines have very high specific speed. And if you link these two to head, normally Pelton wheels have very high, they can operate at very high head, and when you have availability of head is less, then we can refer for a go for a Kaplan turbine. So, that way the judgment is done based on the depending on a locality, whether what type of turbine is best suited at that particular site. Now, let us move on to the first class of turbine, which is called as Pelton wheels. So, the summary is that these are impulse turbines, they are used for high head installations. The main working principle is that whatever available water is there, they are first converted to the kinetic energy in a nozzles, and these nozzles are discharges free jet of water that hits on the bucket, which revolves around a shaft. So, this figure says that we have a shaft, and across the shaft there is a runner. This runner uses the bucket, these are buckets. Now, what we see is that from wherever the water available, and it comes as a nozzle, comes in a nozzle, and this nozzle gives the free jets. So, there is a deflector. So, depending on this keeps on, the deflector position keeps on changing, because the buckets are passed one by one. So, when the first jet of water hits this bucket, so it pushes this runner to rotate, and so that next bucket again gets interacted with this water jets. So, through this process we can have a continuous rotation of this wheel, and that is the reason we call as it is a Pelton wheel. Pelton is the name of the scientist who proposed this concept of this water wheel, and since then it is called as a Pelton wheel. Now, let us try to understand that means in order to make the estimates of how much water or energy is being transmitted to the shaft, we need to explore these velocity diagrams. So, when you see this water jet, we can say that velocity of the water is V1, and it goes as a jet, and this velocity of the water is being utilized to give, since the runner rotates at a rotational speed, and this rotational speed based on the diameter can be considered as a linear speed of this bucket, that Vb we can estimate based on the rotations. So, the total velocity initially when you say it is as a V1 of the jet, and it has composed of two parts, one is Vb and Vr1, and when the water goes out, it comes and hits a jet, and it goes out through this bucket in this fashions, and we have a splitter. So, when the water gets discharged from this bucket, it is ensured that the discharged water does not interact with the inlet water jets, otherwise it will create an interference. So, based on that the velocity triangles can be constructed, one at inlet, this we can say as a inlet, and this we can say outlet. So, through this process we can say that bucket is induced with a velocity Vb, and also we can include this angle beta 2, and in the next diagrams I will show you that how these velocity diagrams is useful for harnessing the power. Now, moving some more deep concept into this water jets, this is another kind of Pelton wheel arrangement which involves multi jets. So, in this previous figure we are showing that there is only one jet which is hitting water, but the concept can be extended, we can have a multiple jets. That means, if you see this is the inlet in which water is coming, and when this water is coming, it keeps on interacting. There are multiple nozzles, and these nozzles are kept through these pier rods, and these nozzles allow the water jets to heat these buckets at multiple locations. and this is what we call as a multiple Pelton wheels arrangements. So, in general we can go up to maximum 6 jets, and through this we can achieve maximum specific speed of 30, and there is a expressions in which we can find out depending on the number of jets we can increase the specific speed for a given for this particular Pelton wheel turbine. That means, initially when you have a single jet we have specific speed relatively less. When we have more number of jets, then we can increase the specific speed for the same turbine. So, that is called as a multi-jet Pelton wheel arrangement. Now, this particular diagram gives you the concept how we can harness the water power, or what is the energy transferred from the water to the turbines. So, for that we have to refer these velocity diagrams. So, let us try to understand these velocity triangles at both inlet and outlet. What we see is your nozzle, and this nozzle gives you velocity V1, which is the absolute velocity of the water jets. So, it has two components, that is bucket component and relative velocity component. So, that means total initially all are in the same line, and when the water goes out, it goes out in a it is deflected by a certain manner, and this deflection is normally kept as 165 degree, and it is the most ideal way. The main reason for keeping this deflection is that when the water goes out or water exists from this bucket, it should not interact the main stream. So, that is the reason, that means VR2 and V1 should not interact each other. So, for that reasons these angles are designed, and optimum angle has been fixed at 165 degree. So, that deflection it ensures maximum power subjected to no interaction of inlet and outlet water jets. Then we can introduce a parameter which is called as a jet ratio. It is a sizing parameter which is the ratio of diameter of the bucket with the nozzle diameters, and its value is in the range of 10 to 24. Now, next thing is that I mentioned about how to quantify. So, velocity of the bucket can be estimated Vb, that is omega times r, that is pi dn by 60s, where r stands as a d by 2, which is called as bucket radius, where an angular velocity omega can be linked to the RPM of the wheel, that is twice pi n by 60. We have the jet ratio d by d, and most important thing here you can say that velocity of the water jet is estimated by using this expression V1 is equal to Cv times square root of 2 gh. So, here Cv is normally the coefficient of the velocity, because as you see that we have the relative velocity do exist between inlet and outlet, that is a loss coefficient. So, that is called as that loss coefficient is accounted in this range. So, this is the standard expressions in which V1 is calculated. Then next important segment is that how to find the energy transfer and work output. The velocity of the jet issuing from the nozzle can be calculated based on the net head available at the nozzle, and the energy transferred to the wheel we can find out using Euler equations. So, the Euler equations can be remembered as E is equal to Vw1 Vb1 minus Vw2 Vb2 by G. Now, let us see what is Vw1 and what is Vw1, Vw2 and Vb1 and Vb2. So, if you look at this particular figure, Vb1 and Vb1 stands for inlet, 2 stands for outlet. So, at the inlet and if you look at bucket velocity, we can think of V1, Vb1 and Vb2 are equal as Vb. So, that drives, that is the linear motion of velocity of the bucket. And coming back to the Vw1 and Vw2, it has two components. If you see the Vw2, what does this mean? If you see absolute component of the velocity in this horizontal direction, we call as a wheel component, and in this horizontal component we say it is a Vw2, and here Vw1 is nothing but V1 itself, because it is purely horizontal component is same as this V1. since the water exists, there is a angle 165 degree, the water goes out at certain angle with relative velocity Vr2. Due to this relative velocity with same bucket velocity, we will have absolute velocity V2 and its horizontal component is Vw2. So, this through these diagrams the Euler equation is been derived, and finally, we come up for this Pelton wheel, we write Vb times Bw1 minus Bw2. Now, let us see what from these velocity diagrams Bw2 can be found out by considering Vr2 and Vb, and this Vr2 it can be expressed in terms of blade friction coefficients, which is similar number because there is a whenever there is a relative velocity, we call this as a blade friction coefficients. That means, there is a difference in the velocity at the inlet and outlet, whether it is in terms of absolute velocity or relative velocity. So, that way Vr2 can be linked with respect to V1 and Vb through a factor k. So, putting these two expressions, we arrive at the energy transferred to the wheel as 1 minus k cos theta by g into V1 Vb minus Vb square. And moreover, emphasis is given that bucket deflection angle is always kept as 165 degree. Now, through this expression of energy transfer to the wheel, one can find out what is the optimum velocity for the bucket, because that is the need of the essential design feature has to be tuned, that how much what should be the optimum velocity at which buckets should move, and that also refers to the maximum energy. For harnessing maximum energy, these expressions can be differentiated with respect to Vb, and so that we can find the E max, that is maximum energy that can be harnessed is 1 minus k cos theta by g into V1 square by 4. So, this one will give that optimum bucket velocity for maximum work output is equal to V1 by 2, which means that bucket moves half of the jet velocity. Now, another expressions are we can find out, or if you look at the what is the efficiency level in which this wheel operates. One term or one efficiency that is defined as hydraulic efficiency. Normally, we call the other synonymous terms are blading efficiency or diagram efficiency, because these efficiency are calculated based on the velocity diagrams. So, we call this as a hydraulic efficiency. It is defined as the ratio of energy transport to the wheel to the kinetic energy of input jet. Now, here based on that expressions, we can first find out what is the energy transport to the wheel. Then by defining hydraulic efficiency, we can introduce the kinetic energy which is in the denominator. So, you take this ratio and define a parameter which is called as velocity ratio, that is Vb by V1. Hydraulic efficiency defined, and subsequently for maximum hydraulic efficiency, one can also obtain that optimum velocity ratio is also 1 by 2, which means that for either you take maximum efficiency or you take maximum work output, the ratio of velocity of the bucket to the jet velocity is always half. So, this gives an indications that bucket velocity, maximum bucket velocity is always half of the velocity in which jet strikes on the bucket. So, this is a very fundamental expressions for a Pelton wheel. What is the, once you know the jet velocity, we can easily find out what is the bucket velocity, and with these design conditions, the Pelton wheel is always allowed to operate. And for this optimum velocity, we can also find out hydraulic efficiency for maximum work, and this also is same as what we have estimated earlier, that is G max is equal to 1 minus k cos theta by g into V1 square by 4. Now, here by closed loop can say that when you say theta is 180 degree, we can have maximum hydraulic efficiency is 1. But in this case, if you do this, then we will have other problem that that means theta becomes 180 degree, which means that the exit velocity also will oppose the inlet velocity, which will have a detrimental effect on the power productions. So, this particular option is always ruled out. So, ideal number that is chosen is theta is 165 degree. When there is a theta is 165 degree, corresponding blade coefficient also is introduced for this theta. So, it falls in the range from 0.8 to 0.85, and this will give a hydraulic efficiency close to 0.88 to 0.91. So, that is the entire idea that a Pelton wheel is allowed to operate. Then the last segment, that once you have velocity, once you have energy, then we can also find out the discharge with known condition of jet velocity and bucket velocity of the wheel, maximum energy output, volume flow rate can be calculated. But there are of course, the Pelton wheels, for large size Pelton wheels also always operates with a multi-jet concept, which can be used for very high head to produce the power maybe maximum range up to 240 megawatt. But there are some side effect of this Pelton wheel, because erosion arises, because this wheel operates throughout the year. So, there is a erosion of the blade that arises, and it also leads to and also there are issues with cavitation of the nozzles. For that reasons, to protect the buckets, typical material of choice is chromal alloy steel or stainless steel. So, these are some of the design features or characteristics, that how many buckets you require for a given wheel and how many number of jets we can have. So, these are the some realistic numbers that are normally used in the hydro power plants. So, this concludes, but before we leave from these lectures, let us try to understand a numerical problem based on this Pelton wheel. So, what the problem statement says, that a Pelton wheel has 2 jets. So, instead of multi-jet, we say it is a 2 jet, that means N is 2, and it works in a net head of 200 meter. It transmits 5 megawatt power while running a shaft at 500 rpm. The transmission efficiency through the pipeline and nozzle is 90%. The jets are tangential to 1.5 meter diameter circle with relative decrement of 10% as it passes through the bucket. Blade deflection angle is 165 degree. We need to find out the efficiency of the runner and diameter of the jets. To solve the problems, we have to refer this particular velocity diagram, in which we can say that initially water jets from the nozzle heats and it splits into 2 parts, and water goes out with a, or water is being deflected by an angle 165 degree. So, to solve the problem, first thing is that we have to recall that what is this V1, which is absolute velocity of the water jet. That is, we can quantify it is k times square root of twice g h. Now, here h is, we have, it is given as 200 meter. Now, k is, we say that there is a relative velocity decrement of 10%. So, k can be assumed as 0.9. So, there is a decrement of 10%. So, k can be assumed at 0.9. So, putting this number, we can say V1 is 0.9 times square root of 2 into 9.81 into h as 200. So, putting this number, we can find out V1 as 56.4 meter per second. So, once we know V1, we can also estimate bucket velocity Vb as pi d n by 60. So, here n stands as 500 rpm, d is the diameter of the wheel. So, here we say that jets are tangential to 1.5 meter diameter circle. So, d can be taken as 1.5 meter. So, putting this number, we can find out bucket velocity as 39.3 meter per seconds. Now, we need to find out what is the efficiency of the runner. So, hydraulic efficiency can be defined as E times kinetic energy of the jet, V1 square by 2g, that is kinetic energy of the jet. So, new denominator part we can estimate. Now, what is this E? That is energy transferred to the wheel. We recall this expression as 1 minus k cos theta divided by g into V1 Vb minus Vb square. So, putting this expression here, this hydraulic efficiency can be expressed as twice times 1 minus k cos theta V1 minus Vb into Vb divided by V1 square. So, by introducing all numbers, we can say eta h is equal to twice times 1 minus k is k cos theta, k stands for 0.9 cos theta into V1 is 56.4 minus Vb is 39.3 into Vb, that is 39.3 divided by 56.4 whole square. So, this will give you hydraulic efficiency as 83%. So, the first part of the answer we got, hydraulic efficiency of the runner is 83%. Now, let us see that how we need to find out the diameter of the jet, because we know there are two jets. So, one can say how much power we can develop, because the turbine transmits 5 megawatt power. Power transmitted is 5000 kilowatt. So, power developed would be P is equal to this 5000 divided by this hydraulic efficiency, and that is equal to 6024 kilowatt. And this, since there are two jets, for power developed per jet would be P by 2, that is 3012 kilowatt. The power developed per jet, we can write it as half m V1 square, which is 3012 into 10 to the power 3. Now, what is m? Is rho into A into V1. So, here A stands as pi by 4 into d square, d stands as the diameter of the jet. So, we can rewrite this equation as half rho A V1 into V1 square, that is equal to 3012 into 10 to the power 3. So, you know what is V1? We have A as pi by 4 d square. So, putting this number and density of water. So, rho as 1000 kg per meter cube. So, putting this number, one can find out diameter of this jet as 0.2 meter. So, the nozzle produces a water jet of diameter that is equal to 0.2 meter. So, for this diameter, this hydraulic efficiency is 83% and it transmits the power 5 megawatt while running at 500 rpm. So, with this I conclude. Thank you for your kind attention.